Next speaker, who is Anita de Ruiter. She is working at Book University in Vienna in Chris Ostenbrink's group as a postdoc, and she will be talking about multi-site AEDS today.
Yes, thank you, Mark. Indeed, so today I will be talking about multi-site AEDS. Well, I don't have to introduce here free energy calculations, but it seems that there are a lot of talks about FEP. This time I will be talking about slightly different methods. So we use AEDS, stands for Accelerated Enveloping Distribution Sampling, which is basically where you just do a single reference simulation in which you try to sample all relevant phase space of the end state of the Hamiltonians. So for example, if you want to calculate the free energy differences between a lot of ligands, then each ligand would be an end state. And if you want to, so the way we generate this reference state is by combining all the Hamiltonia of each of the ligands in such a way that we do use a Boltzmann weighting. I will show it in a minute in a different, if it wants to continue. So let's say we have, in blue we have a state A, is one particular ligand. In red we have a different one. And we want to make, we want to generate a reference state which encompasses all these ligands. What we do is basically, with this formula, is basically taking the minimum of both of these states. We do see here that we have a slight problem here. So if we're going to sample along this energy landscape, we will get stuck here. We will never get in this one because this has a much higher energy. So we want to pull this one down such that they have both the minima at the same level. This is what you see here. So this purple thing here is the free energy offset, which we see back here in this figure. Now the only problem that we have here is that we have this reference state, this barrier is way too high to even to cross. So we want to lower this. This we're going to do. We have to set a few parameters. So we have an Emax, that's the maximum barrier that you see, and we have an Emin. And this is actually the acceleration part of it. Before it was still only EDS, now it's the acceleration. You lower this barrier here. The nice part about the accelerated EDS is that the minima are actually not shifted in space. So before, the original EDS was such that there was a smoothing parameter in it, which could actually shift the minima in space, which we don't have here. So in this way, we would have a way to, based on just on the Hamiltonians of the end state and a few parameters which you can search for in an initial search run, we have generated a reference state which encompasses all the Hamiltonians in the important phase space of all the end states. So what can we do with it? Like I said, we can use it for protein ligand systems. We cannot just do it for two ligands, but we can do a whole lot of them at the same time. And what we've already seen today, what is of interest in the field, is that when that water molecules in binding sites can play an important role. Right. So we have an example here, which is in a heat shock protein where we have these two ligands that are very similar, but in this case, both of them have crystal structures, and in this case, there are two water molecules present. In this case, according to the crystal structure, there is none present. A previous PhD student from our group actually did these calculations, and we were trying to reproduce these results. So actually, what he did was using AEDS on the water molecules, and what he found is that indeed these were present. In this case, this one water was displaced, but the other was actually present. So let's see if, well, let's look more into detail of this. So basically what we're going to do here is use AEDS as a chemostat for water. So we determined the EDS parameters, so this Emin and Emax and the free energy offsets for one water molecule in a bulk water. So it's very simple. You get a solvation free energy, which makes sense. Then we have the, if we have searched for these parameters properly, then the sampling should be such that you have 50% as water and 50% as dummy atoms. And then we can use it in the protein and see if we have more or less of this water present. So like I said, so the experimental values, the delta G is represented here. If we would take into account that ligand A has 2 waters and ligand B has 2 waters, then we will get this delta G based on a TI. If we have, we can do all kinds of combinations. You will see that they're all pretty wrong, except for this one, where we have 2 waters here and only this water here. So the prediction from the AEDS was actually correct if we look at the thermodynamic integration part. But I said I was going to talk about multi-site AEDS and not just AEDS. So with multi-site AEDS, we don't want to just look at 1 water or 2 waters. With more waters, it would actually get very complicated just with a single AEDS. What we want to do is we want to have multiple sites. So we want to be able to do one AEDS site would be the ligand, and the other one would be the water or the dummy, or actually even more. For this, we have to store a lot of interactions. So we have to look at ligand A interacting with ligand A. That's okay. But if you're looking at your first AEDS site, it actually interacts with another AEDS site as well. But you don't know at this moment if this is actually rather wants to be a water or a dummy. So we have to calculate each interaction. And of course, also with the non-AEDS. So we have to determine all these energies and store them. We store all these possible interactions between all the possible end states of all the sites. And then we need to enumerate all possible combinations of states. So in this example before, where we have either a ligand A or a ligand B and a water or a dummy, we have only 4 possibilities. That's still doable. It can get a lot more complicated quickly. Now, for these 4 possibilities, for these combinations, we have to determine which is currently, so at the current simulation step, what is the optimal set. So we calculate all the interactions, like we assume that the first site is now a ligand A and the second site is now a water, determine the energy, do it for all of them, determine which one is the optimal. And we mark it with the star. Now we didn't do any actual calculations yet, we just determined which one is now, at the moment, the optimal state. Now we're going to do the calculation for we want to calculate the energy for the first site. So again, that would be the energy with itself and with the rest of the system. Also with the other, if we're looking at the interactions between one site and the other site, for the other site, we're going to assume that it is now in its optimal state, as we just defined before. And then we can just continue for all the sites and states, sum over them. And then what's also important to mention that each site will have its own Emin and Emax and the offsets for each of the states. And we apply this acceleration separately for each site. So if we now apply this to this example that we saw before with the Woodhead ligand, we are going to say site 1 is our ligand. Our second site is now this water molecule that was displaced for the second ligand. And we've determined like the different parameters, so the Emin, Emax, and the offset. We determined separately based on a regular AEDS simulation, separately for the ligand, just in water and just a water molecule in bulk water. And what we see if we run the simulation is that the majority of time it's actually in this particular state here. So it's with the first ligand with the water here, which is like sampled for 95% of the time. The other sites are not sampled that much, but we do see that if we are sampling the second ligand, then we actually have a dummy in this site, as we were predicting before. And we can actually also calculate the free energy difference between these two. We get 64 kilojoules per mole, whereas the TI was 60 kilojoules per mole. Where, of course, the TI took way more computational effort there, so just our 10 nanosecond simulation of the AEDS. But we can expand it even a bit further. So we're now going to make 3 sites. So this would be more if you wouldn't know in advance if how many water molecules or which water molecules would be disappearing in your active site. So we just have the ligand again. Now this is a separate AEDS site, and this is a separate AEDS site. Again, we have searched for the Emin and Max already. So if you did this once for a water molecule, you don't have to do it again. It's always the same. And again, we do the multi-site AEDS simulation. Now, of course, we have a bit more states. Again, we see that we are mostly sampling the one where we have the first ligand and the waters at both of these sites. And if we are sampling the second ligand, then we're mostly sampling the ones that exactly the one that we saw already before. So this shows that our multi-site AEDS is actually working, and it can, during the simulation, predict which water molecules want to be present in your binding site. Again, we can also do the free energy calculation there, which is 70 kilojoules per mole, which is still a bit off. But so we have a second test system, which is a bit more challenging, I would say. So we have basically 2 aspartic acids based on the conformation that was found in the HIV protease. But we are really still in water. So these are just these 2 molecules in water, and we have positional restraints on the carbon atoms here. We're going to sample a lot of 5 states for each, so it can be completely deprotonated, or it has hydrogen on one of these 4 points. So here we have really 25 possible combination of states. And again, the Emin, Emax, and offsets were determined for a single molecule in water. So do we sample all the combinations of states? No, we don't, actually. But what we do see, this bottom one here is when both both molecules are deprotonated, so it's not very favorable. what we see is that the first molecule is deprotonated 88% of the time, and the other one is then protonated at one. So these ones. It's not so often that the second molecule is actually deprotonated. That's only 12% of the time. But when it is deprotonated, then it samples. The first one is then protonated. This actually is similar to what we know from the HIV protease. So there's only one aspartic acid which is deprotonated at a time. We would have expected a little bit more switching between the deprotonated states, such that they are both 50% of the time deprotonated, but maybe it's a bit too much to ask. Maybe the environment plays a role there, then that it's a bit too slow to react. And I think, so I have still some sampling times here that are not that important. I have some free energy differences here, where you're basically switching the proton from here to the other molecule. If that makes it different, it doesn't matter that much. If you're really changing the protonation of one of them, then you have a huge energy difference as expected. So to conclude, we've implemented the multi-site AEDS into the chromal simulation package. We use the AEDS parameters for single site, such that we don't have to repeat the search runs. And the outlook is, well, we need to do quite a bit of testing. This is very much a work in progress. When we could continue to do it in the actual HIV protease. And also, very importantly, we want to apply it as, we want to do constant pH simulations with that, so that the histidine is, for example, all the histidines are separate AEDS sites, that the simulation itself can decide if this histidine should be protonated or not. And with that, I would like to thank you for your attention.
All right, thank you, Anita. Are there any questions?
Hi, thanks for the presentation. In the water there or not, your waters seem to be integer waters that are either in the site or not. How do you handle them exchanging or going to other positions?
There's a slight distance restraint on them that they keep in place.
Hi, sorry, thanks for the talk. I am a little bit confused, maybe it's because I don't know this method. So when I see the sampling, I understand that from your modification of this bigger Hamiltonian, you would actually be able to sample way more of the states, and you actually show that you're basically just stocking one. Is not, so where is the acceleration per se? Like, I think that, do you reweight these states, or how do you actually know that you have sampled enough all the other states? Because I mean, most in the numbers that you presented, which I assume is after some post-processing, most of the states seem to be just focused on one.
Sorry, what do you mean with most of the states are sampled on?
For example, in like for the 2-state or 3-state system, it turns out that you are normally just sampling one state and very few of the other one.
Yeah.
My point is, like, are you sampling also frequently of the other state, so you actually can do like these statistics? Or are you in this single simulation just seeing this crossing event once or twice?
It's not, well, we're not seeing it that often, that's true. And that leaves a question if how accurate your free energy difference is there. But we do see it a couple of times, yeah. So it is, we have some data. I'm not saying that we have enough to be a very accurate results yet at the moment. That's because we take these these parameters from a search run in water, basically. So the environment changes. That's why this it gets more difficult to sample then.
Okay, I think for time reasons, we are going to move on to the next speaker, who is Andrea